Okay, this is video 2 for the kinematics unit. All right, in this video, we're going to start by talking about constant acceleration. Acceleration is defined as a change in velocity over time. So let's say something has a constant acceleration of 4 meters per second with an initial velocity of 0 meters per second. What that means then is at 0 seconds, the object has a velocity of 0 meters per second. At 1 second, its new velocity is 4 meters per second. 2 seconds, it's now 8. 3 seconds, it is now 12. 4 seconds, it's now 16. So again, hopefully you notice that there's a relationship here. If the acceleration is constant, then for every time interval of 1 second, the object's velocity changes by the same interval. So whether we're going from 1 to 2 seconds or 4 to 5 seconds, the change in velocity is still 4 meters per second. And I also hope that you notice how this is very similar to the constant velocity we discussed in the previous video. So let's go ahead and graph this. Again, this is a 20 by 20 square. So over here we have velocity measured in meters per second. Then down here we have time measured in seconds. Okay, so let's go ahead and plot this data. So 1 second it was 4, 2 seconds it was 8, 3 seconds it's 12, 4 seconds is 16, 5 seconds is 20. All right, again, hopefully you can see that this is a nice linear relationship. So I'm going to freehand this. I want you to use a ruler. It's not perfect, but I'll go with it. Now, once again, once you see a graph, figure out what the slope means and figure out what the area means. So let's start with the slope. I'm going to choose a couple points on this line. I'll go with this point and this point. They look convenient. So this up here is 15 meters per second. This down here is 5 meters per second. 3.5 seconds. 1.25 seconds. So the slope, 15 meters per second minus 5 meters per second. Pull out my handy dandy calculator. So that's going to be So I'm getting 4.4 repeating. Again, I freehanded this, so this is pretty close. We should have got 4. That's pretty close. So what that tells us then is that the slope means acceleration. And we could say that the acceleration then would equal final velocity minus initial velocity over final time minus initial time, or that the acceleration equals delta v over delta t. So that's our acceleration right there. Area. If I were to take a look at area under this line here. Well, again, this is a triangle, so it'd be like 1/2 base times height. So it would be a meter per second times a second. That's a meter. So this time, the area does have meaning. The area gives us the displacement. Now we have to be careful. It is displacement and not distance. It has to be displacement. All right. Notice then that the slope means two different things depending upon the graph. Because last time slope meant velocity, but that was on a position graph. If we were to make a position versus time graph, constant acceleration would look something like that. Now this right here is actually positive acceleration. This is negative acceleration. Smiles have positive acceleration. Frowns have negative acceleration. And then if I were to look at an acceleration versus time graph, constant acceleration then would be our horizontal line. Okay, so as I said before, the area under the line on a velocity time graph is the displacement of the object. So let's take a deeper look into that. Let's say I have something that is going from an initial velocity to a final velocity. And we have our initial time and our final time. Notice that we can break this up into a triangle and a rectangle. And the area of a triangle is 1/2 base times height. Area of a rectangle is length times width. So that means that the displacement here would be length times width. So this would be our V naught minus 0 times, I'm going to go say delta t. And the triangle would be 1/2 the I actually do height minus base, so it would be delta V delta t. So our displacement would look like that. That's one way of calculating displacement. Remember that acceleration is delta V over delta t. So what we could do is I can delta V equals a delta t. I can plug that in for my velocity up there. And that gives me this equation here. This is a very important formula. This one's universal. It works for both constant velocity and constant acceleration. So it's a very, very important formula. All right. Let's go ahead and let's do a little bit more math here. Let's go back to our equation. And let's go ahead and do what it tells us. Let's go ahead and take that delta V out. And let's just continue on with the algebra. And notice that here I have basically 1 V naught delta t, and here I got negative 1/2 V naught delta t. So clean this up then. That gives me another equation to find displacement. Okay. Now, using the universal equation, I'll rewrite it just slightly. Notice that this is a parabola. So if I were to make a position versus time graph with this data, it should look like that. So it just further explains why acceleration looks like a curve on the position graph. Okay, let's say we have a velocity graph that's not a straight line. It's a changing one. Well, once again, the slope of the tangent line would be the acceleration. So here, I have a negative acceleration. Down here, I have 0 acceleration. And then right here, I have a positive acceleration. This also means that once again, we get to use some calculus. The acceleration will be the limit as time approaches some number of delta v over delta t. So in other words, acceleration would equal dv over dt. But remember, v is dx over dt. So that means that acceleration would be dx over dt over dt. Or I can rewrite it as second time derivative. All right, now here what we have is an acceleration time graph. And again, we want to look at slope and area. Okay, the slope of this line, that would be meters per second divided by second. You rise over run. That is meter per second cubed. That has no meaning. So on the acceleration graph, the slope has no meaning. Area, however, would be meter per second times second. Well, that's a meter per second. So in this case, the area equals change in velocity. Now I can't say that enough. It's not velocity, it has to be the change in velocity. All right, another topic that's useful is average velocity. If you're in a car going from point A to point B, as you're driving, you're not going to maintain a constant velocity the entire trip. You're going to have to speed up, slow down. You're going to encounter stoplights, changes in posted speed limits. There's a lot to it. So what we may be interested in is just what's the average velocity? If I'm going from one velocity to a second velocity, is it like that? Is it like this? How can I get that? Well, to find the average velocity, we just find its average. I mean, it's like finding the mean of something. Add them up, divided by 2, because there's 2 items in the set. Well, something else. The delta x over delta t formula. That can also be thought of as a average velocity. Because if the velocity is constant, if the velocity is unchanging, you're looking at this equation up here. If v naught is equal to v, you would just get 2v divided by 2, which equals v. So we can do a little bit of algebra with this. So if I do that, I'll leave it up to you, but here's what you should get. An equation that we've already seen before. So as an exercise, go from here to here. All right, now we can start putting all this together. Using these equations, we can derive another one ending up with a fourth kinematics equation. So we can have 4 kinematics equations for constant acceleration and 1 for constant motion. So if I go to this equation, and if I were to use my acceleration equation, I can solve this for delta t and plug it in up here. And then, doing a little bit of algebra, got a binomial here. Hopefully you can see that we would get that right here. So, when we have constant acceleration, we get to use these equations. When we have constant velocity, we're a little more limited. What's left down here, if you want to, you can pause this, is just those motion graphs. It's something that you really should go back through and familiarize yourself with. All right, well, that concludes this video.